Good morning, friends. As you all know that we are going to venture into the concepts and understanding of aircraft dynamic stability, and we need to know the purpose of this course. In the last lecture, I have given you a brief indications, but let me be a little bit more focused. And when I write purpose for this course title, primary title, aircraft dynamic stability, purpose, if I write, the purpose is to understand the dynamic stability is of course there, and what goes along with dynamic stability is the response of the airplane. So this response and dynamic stability, they are somehow linked. Okay, and if we talk about dynamic stability, immediately something will come to your mind, how the airplane is going to respond, or in more precise term, how will be its transient, right? That is what we look in aircraft dynamic stability. However, we would like to see its dynamic stability behavior or a response when the aircraft is disturbed from its equilibrium, which goes along with the definition of dynamic stability. Its response when it is disturbed from the equilibrium, but what type of disturbances? It's a small disturbances. So that should be kept in the mind. That is, I would like to study dynamic stability of the airplane in terms of small perturbations about steady state, about the equilibrium state. And you all know that cruise could be one of the steady state. It could be a steady climb, also could be a steady state. But mostly we'll be focusing around a cruise. So what is the understanding? We want to see the response of the airplane when the airplane is given a small perturbation about its equilibrium state. Okay. Now, so what is dynamic stability? If I try to now again revisit, dynamic stability is the tendency of the airplane to ensure that the disturbed amplitude, that is when the aircraft is suppose moving in a cruising at a steady state, and if I give a small disturbance, say in terms of angle of attack, and if this disturbance is withdrawn, I would like to see how the airplane is coming back to the equilibrium state, right? And this part will be addressed all throughout in our dynamic stability analysis. Okay. For example, you know, if I say something is dynamically stable or a system is dynamically stable, graphically I show it like this, that if I give, this is the, let's say this is the disturbance, so I have given a disturbance, and if I withdraw the disturbance, whether it comes like this, whether it comes like this, whether it comes like this, the question is how its transient is behaving with respect to time and whether it is coming back to its equilibrium or not, right? That is the area where we will be addressing under the umbrella of dynamic stability. If a system is dynamically unstable, then if I have given a disturbance, it may do like this, it may go like this, it may go like this. All are simply representing the system is dynamically unstable, because in finite time, the disturbed element or disturbed motion variable is not coming back to the equilibrium. Okay. There could be a case where, let's say this is the disturbed quantity, and this is time, and this man goes on oscillating like this. You see that the amplitude is not increasing, but it is going on oscillating. So it is actually speaking dynamically, neutrally stable. Okay? Right? So these sort of cases we will be discussing, and this sort of understanding of the definition is required. And what is the response here? This, how this x is changing with time, that is the response. That is the transient for our case of analysis. Right? Please understand, when I write xt, this is the disturbed variable, in a sense, or perturbed variable. In a sense, suppose the airplane was flying at alpha equal to 5 degree, and it was maintaining a cruise. Okay, I give a small disturbance in alpha, say maybe 0.5 degree of disturbance I give. So this xt is 0.5 degree. Now, if it comes like this, I say the disturbed quantity is vanishing once the disturbance, which is causing the disturbance, is withdrawn, and is coming back to the same. Let's say this was alpha equal to 5 degree, and this xt is alpha, and this line equilibrium was 5 degree. So it is again coming back to 5 degree. So that shows the aircraft is dynamically stable. Okay. If we see the similar example for a mass spring damper system, so once I disturb it, this distance is xt. This is the perturbed quantity, small perturbation. Right? The perturbation should be such that there should not be any gross change in the whole system behavior. In a sense, I should not stretch it so much that the spring constant will change, the length of the spring will change, material cross-section will change. All these things are not allowed. Okay? That is a small disturbance. And as I release this, then it comes back. Again, you could see it comes back to the equilibrium, which is here. Then I say the perturbed quantity, or xt, has vanished. It has become 0. It has come back to the original equilibrium condition. So then you say this is dynamically stable. Okay? So you could see that when I am talking about dynamic stability for aircraft, suddenly I am forced to bring this mass spring damper system for discussion. Why this is so? Let us also try to understand. Before I go to that, let me write classical definition for response, and you should know this. Although we have discussed as a matter of understanding, let me write the classical definition. It is defined as the change with time. So I am putting it in block letters, with time of motion variable relative to some, again I am writing this, some steady state flight conditions. As a result of an externally or internally generated disturbances. Very important. For aircraft, we'll try to understand this term. This is clear. It is defined as the change with time, that is, we are talking about time history of motion variable. What are the motion variables? When an aircraft is moving like this, one of the motion variables is angle of attack, one of the motion variables is Q, pitch rate, should be speed, so many things, right? Motion relative to what? Relative to some steady state flight conditions. Let's say we have taken a cruise. At cruise, it is flying at an alpha or angle of attack of 2 degrees. And the disturbance has caused, say, additional 0.1 degrees. We are seeing how this 0.1 degree is changing with respect to the steady state, which is 2 degrees, right? So relative to steady state flight condition, why this has come? As a result of externally or internally generated disturbances. What is the externally generated disturbance for aircraft? I am moving like this, suddenly there is a huge cloud is coming, or huge density variation is there, right? There may be upward gust, turbulence. So they become external disturbances. Now what about internal disturbances? So I could always try to change from one equilibrium to another equilibrium by giving an elevator input. additional elevator input. Suppose I am moving at alpha equal to 3 degree and I have given delta is 2 degree. Now I have to go to alpha 5 degree, so I have to increase the elevator angle. So now from the steady state, another 2 degree I have given or 3 degree I have given. So that is a internally generated disturbances, right? In all the cases, it should have tendency to come back to the equilibrium once this is withdrawn. That's the important thing. Okay? So that is why I thought the response part I should write carefully so that you know what is happening. Now I come back to this statement whenever I am talking about dynamic stability of airplane, why I am bringing mass spring damper system. Okay? So let us first understand that. If I come to mass spring damper system, mass spring damper system, you know, typically the diagram, if it is, let me draw it like this. If this is mass M, and there is a K, and there is damper. This is K. You know, as I stretch it, this mass, so there will be a restoring force Kx. Kx is the disturbance, small perturbation from the equilibrium, right? So this will try to take it back to the equilibrium, right? So there is a restoring force proportional to, so I write restoring force proportional to displacement. Also, you know that there will be a restoring force proportional to the rate of change of this small disturbance, and this is we call damping. And C is called the damping constant. Please understand here, damping is basically is part of friction damping we are talking about. That means energy is lost because of friction in terms of heat, primarily in terms of heat, right? And there is another assumption that we are talking about linear damping. That is, this is Cx dot. It's linear. Not, there could be non-linear damping also. But we are talking about linear damping, and we are having the liberty to assume it linear damping because we are talking about small perturbation. Okay? So what is understood here? If this is the mass, there is one restoring force as soon as you try to take it out from the equilibrium condition, and also depending upon what rate you are taking it out, there will be again a restoring which is damping in nature. These two combined will try to oppose this motion or try to bring it back to the equilibrium, tendency to bring it back to the equilibrium, right? Now, think of an airplane. If I see an airplane, and I am sure you have done your second course on static stability. You remember Cm versus alpha. What was Cm? Cm is the pitching moment coefficient. So let me write it here, Cm as pitching moment coefficient, and which is defined as pitching moment non-dimensionalized by half rho v square s c bar. All these things you know. And what is the convention of pitching moment? That nose down is negative, nose up is positive. Clear? And to be more explicit, if I draw the airplane like this, if this is the x-axis, and if this is the y-axis, and this is the z-axis, which are body fixed axis, pitching moment means motion about y-axis. Nose up is positive, nose down is negative. Now, coming back to the static stability for airplane, we realize that if there is a disturbance delta alpha, right, that is let the airplane was moving at this equilibrium, and suddenly there is a delta alpha. Say 5 degree it was flying, suddenly there is 0.1 degree of disturbance. Then dynamic stability will tell that in finite time, it should come back to 5 degree. Okay, once the disturbance is withdrawn. So, if this is more than the 5 degree, it should generate a nose down moment, right? We all know that, and that is how we draw Cm versus alpha, and the slope dCm by d alpha negative, right? If at equilibrium dCm by d alpha is negative, we say the body is statically stable. No doubt about it. You can again cross check here. If the airplane is flying at this stream, why this is stream? Why did you define this as stream? Stream means the Cm is 0. Airplane is going like this, no such motion, going, cruising like this. So pitching moment is 0, and of course for a cruise, thrust equal to drag, lift equal to weight, net force is also 0. So now suppose the airplane is flying like this, because of some disturbance, angle of attack has increased. So what this slope will tell you, it will immediately generate this negative pitching moment. So the airplane, if alpha has increased because of some reason, airplane will give a nose down moment. And that is the significance of dCm by d alpha less than 0. But what is the meaning? Meaning here is, please understand, when I write Cm as Cm naught plus Cm alpha into alpha, remember that is dCm by d alpha into alpha. So if this is negative, this contribution is a restoring moment, like you have for a spring case k into x, the restoring. You see, alpha is the displacement, x was displacement. So the restoring force for a spring, here restoring moment for the airplane. So this is Cm alpha into alpha or kx into kx, they are analogous. They are like a spring action. That is why you will see that with Cm alpha, we try to relate the stiffness of the airplane or longitudinal stiffness of the airplane. Because in a spring K, we always talk in terms of spring stiffness, right? So there is a similarity for a statically stable airplane because of Cm alpha into alpha. Now, what about damping? Let us see about damping now. These things we have discussed in my second course. You might have seen that, but I'm just revising it so that you feel comfortable. This is the tail, right? And let's say this is the CG. And let's say the airplane is going for a pitch up Q. As it goes for a pitch up like this tail goes down. So there is a relative air speed, which I can write Q LT by V, and LT is the distance between CG and the AC of the tail, right? QLT omega r, and it's moving forward, V. So this is the angle of attack introduced at the tail because of pitch rate. Now what this angle of attack will do, this will give a force in this direction, which will give a moment in this direction, and the moment here will be proportional to half rho V square SC bar CL alpha tail into Q LT by V, that is alpha, into LT. That is the moment will be generated by the airplane because of Q. Now you could see this is also restoring moment because the airplane was disturbed for a Q like this, but this tail will try to put it down. So it try to restore it, and the restoring moment is proportional to the rate, not to the alpha, but to the rate, pitch rate. So this is also M damping, right? Earlier was M, Cm alpha into alpha was stiffness. So this is damping. This is analogous to C x dot. X dot is nothing but, it is like Q. So I see that the dynamics of an airplane can easily be modeled in a restricted sense if I understand a mass spring damper system. Right? Is it clear? So that is why we always give example of mass spring damper system before we come to aircraft dynamic stability. As far as these derivatives are concerned, you already know, and I'm sure when I talk about damping, you should recall there's some derivative called CMQ. Like for stiffness, we have CM alpha. CM alpha means dCm by d alpha, and CMQ means dCm by dq c bar by 2v. Don't worry, we'll be again deriving these derivations so that you understand in complete. But to build this course, I like to orient your mind and see what is our roadmap, where you are going. The basic question is, why for an aircraft I am giving this example of mass spring damper system. Remember one thing, very important, in a mass spring damper system, there is a stiffness, that means the restoring force is proportional to the displacement. Similarly for aircraft, restoring moment is proportional to the angle of attack, which will lead to displacement. Also in a spring mass damper system, restoring force is also proportional to the rate Cx dot. Similarly for airplane also, restoring moment damping is also proportional to the rate, which is q pitch rate. And here we write it as CMQ into QC by 2V. So these are the restoring tendencies, and because it has both, restoring moment has both function of displacement as well as rate, so this is attributed towards the stiffness, this is towards damping. And there lies the similarity, there lies the necessity to understand the mass spring damper system dynamics. Once you understand that thoroughly, we come back to aircraft again. Is it clear?